Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering. And this is a review module where I talk about the concept of maximum power transfer. And often when we're designing circuits, actually I would say maybe even usually when we're designing circuits, we're designing a circuit to drive some kind of load. So for example, we might be designing an amplifier and connecting it to a speaker and using that amplifier to drive a speaker. And our circuit often has internal resistors, right? And so ideally we would like 100% of our power to be delivered to our load. But any circuit will have internal resistance, and when we do have internal resistance, some waste power will be dissipated by the resistors internal to our circuit. And so the question is, how do we, given that internal circuit resistance is kind of a fact of life, how do we deliver as much power to our load as possible? And this is what the maximum transfer power theorem, or the notion of maximum power transfer, is all about. And the concept of maximum power transfer is very much tied to the notion of the Thevenin equivalent circuit, or finding the Thevenin equivalent for our circuit. And so typically we have some kind of circuit, and for now I'm just going to draw it as a black box. And it is driving some kind of load, and I'm just going to model the load as a resistor. And so let's assume that RL represents our speaker, or represents our light, or whatever sort of useful thing that we're trying to drive with our circuit. And so the total power delivered by whatever energy source we have in our circuit, some voltage source or something like that, will be equal to the power dissipated in the load, which is, this is the desired power. This is doing useful work for us. And we also then have a waste power term. And the waste power is being dissipated by the resistances internal to our circuit. And so what we want to do is to represent our circuit using the Thevenin, its Thevenin equivalent. And I'll review Thevenin equivalents here in a second. But basically our internal circuit is modeled by a single voltage source and a single resistor in series with that voltage source connected to our load. And so basically this black box can be represented by the two components inside this dotted box. Okay, so Thevenin's theorem then is such that this Thevenin equivalent voltage is equal to the open circuit voltage seen at the load terminals, and the Thevenin resistance is the equivalent resistance seen from the load terminals. And just to make it kind of more clear about what we mean by this, let's do an example. So let's consider this circuit where we have R1, R2, and then some load. And let's represent these two nodes as our load terminals, and then we want to find the equivalent, the Thevenin equivalent, for everything inside this dotted box. Okay? And so the Thevenin voltage then, if, I guess maybe I'll just use my eraser here. So if we remove the load resistance and just replace it with an open circuit, then the Thevenin equivalent voltage is the open circuit voltage at the load terminals. And so in this case, with that load being open circuited, the Thevenin equivalent voltage can just be found using just the voltage divider equation. And the Thevenin equivalent resistance, in contrast, is found by replacing all voltage sources with short circuits. And so if we replace this voltage source with a short circuit, we still have R1 and R2. And so our Thevenin equivalent resistance is the resistance of these two resistors with respect to our load terminals. And of course, when we short circuit our voltage source, we just have R1 and R2 in parallel. And so our Thevenin equivalent resistance is just equal to R1, R2 over R1 plus R2. And this is the general technique for Thevenin equivalence, right? So we just pull out that load resistance, figure out the voltage across the load resistance, that's the Thevenin voltage, and then short any voltage sources we have and figure out the resistance with respect to those terminals, and that's our Thevenin resistance. So this is the value that we would plug in for this source, and this is the value that we would have in series with that source. All right, if we draw now, or I guess redraw our Thevenin equivalent circuit, we've got our Thevenin resistance in series with our load. The current flowing through our loop, we just represent according to I. And we want, or we can write, the power in our load as being equal to I squared times the load resistance. And if we want to solve for I just with Ohm's law is equal to the Thevenin voltage divided by the summation of the Thevenin resistance and the load resistance. And so we have V Thevenin over R Thevenin plus RL squared times RL. Now, what we basically want to do is figure out what value of load resistance is going to maximize the power dissipated by the load. And so this is kind of where our design question comes in, right? So we're designing this circuit, it's completely under our control, and we know we can't completely eliminate the internal resistances to our circuit, but let's say we have some control over what our load resistance is going to be. And we want to figure out what value of load resistance we should choose in order to maximize the amount of power that's delivered to that load. You can do this problem the other way. You can say, okay, well, my load resistance is fixed, and but maybe I do have some control over the internal resistances in my circuit. So you could solve the problem that way. But basically, for the purposes of this derivation, we're going to assume that our Thevenin is fixed and the load is under our control. And so how do we figure out the value of RL that maximizes the power delivered to the load? Basically, we're going to take the derivative of P load with respect to the load resistance and set that equal to 0. And so if we do that, DRL, we can take the Thevenin voltage squared and just pull it out because it's not a function of RL, so it doesn't affect the derivative. Then we have the derivative of our Thevenin plus RL to the exponent of minus 2 times RL. And if I just use the chain rule, this ends up being equal to Thevenin voltage squared 1 over R Thevenin plus RL squared minus 2RL R Thevenin plus RL cubed. And I'm going to put that under a common denominator. and set that equal to 0. And so when we set it equal to 0, we can get rid of this term, we can get rid of this denominator, and then we just have R Thevenin plus RL minus 2RL is equal to 0, which gives us the result R Thevenin equal to RL. And so basically, if we want to deliver the maximum amount of power to our load, we have to set our load resistance equal to the exact value of the Thevenin equivalent of the internal resistances of our circuit. And how does this work exactly, or what's sort of the intuition behind this result? Well, I always kind of like to understand it in terms of, even though we started the derivation with the current squared times the resistance equation for the power of the load, we can also write the power of the load, is equal to the voltage across the load squared divided by RL, right, where, I guess, that's VL. And thinking about that voltage equation for power, let's imagine a graph where we have the value of load resistance on the x-axis and P load on the y-axis. So if RL is equal to 0, then there's no voltage drop across our resistance and our power is equal to 0 as well. And so we want to increase the amount of our Thevenin voltage that drops across our load rather than our internal resistance. And so as we increase our value of RL, for a while, power is going to increase as well, because as we increase RL, we're getting a larger share of the Thevenin voltage. However, what's going to happen is we're going to hit a maximum, and then our power is going to start to drop down after a while. What happens to cause this decrease is because if we make RL too big, then we're basically reducing the amount of current that can flow through this loop, and our power starts to drop because of this current equation. And it just happens that this maximum occurs at the Thevenin resistance.